These renderings are based on the actual information flow patterns estimated from real brain data. Here is how it was done. Let us start with fMRI. fMRI is a brain imaging method that measures changes in blood oxygen levels, which we use as an indirect marker of neural activity. Here, you can see a slightly sped-up resting state fMRI signal mapped onto a 3D brain. The red regions show higher neural activity, while the blue regions show lower activity. To go from this raw signal to something about information flow, we use a technique called regression Dynamic Causal Modeling, or rDCM. First, we divide the brain into about 400 regions of interest, or ROIs. For each ROI, we extract a single fMRI time series. rDCM then takes all these time series and fits a generative model that estimates how strongly each region influences every other region. The result is this rDCM matrix. Each pixel corresponds to a directed connection from one ROI to another, and its color reflects the effective connectivity strength between those regions. Here you can see what this rDCM matrix really looks like. The pattern is dense, and many pairs of regions are bidirectionally connected, which makes it hard to see where information is actually flowing. Here is the same rDCM matrix, but now mapped back onto the ROIs in the brain. You can see it becomes quite messy. There are many overlapping connections, and it is still difficult to get an intuitive sense of the main information pathways. In that ROI-mapped rDCM view, I showed connections as straight lines between regions. Of course, this is not how things look in reality. Information most likely travels along curved white matter pathways between regions. To see how regions are physically connected, we use a technique called diffusion fMRI tractography. Here, you can see what these white matter tracks look like. A dense bundle of streamlines approximating the major fiber pathways in the brain. Now we can combine the two. We fuse the rDCM connectivity with these diffusion tracks. Conceptually, for each streamline connecting two ROIs, we use the corresponding rDCM connection strengths to weight that streamline and give it a preferred direction. This gives us a 3D representation of where information is likely to flow, constrained by both effective connectivity and actual white matter anatomy. As you saw before, the rDCM matrix mapped onto ROIs was already quite complex and hard to interpret. Fusing it with all these white matter tracks adds even more detail, so it becomes even harder to see the main flow patterns by eye. To make sense of this, we use a neural network called a mixture density network, or MDN. Here is a simple toy example of how it works. We start with a very messy particle flow, where each particle seems to move in a random direction. We then train our MDN on the paths these particles take. The MDN learns an underlying 3D vector field. It is basically guessing. If particles followed these paths, what smooth field could be generating them? The resulting field is smoother and highlights the dominant flow directions. The whole point of the MDN is to smooth the data and focus on the main, consistent flows. This is great for visualization, but it also means we intentionally ignore very rare or subtle paths. So you should interpret these flows as a useful visualization of dominant information pathways, not every possible route. And this is the final result of the pipeline I put together. It combines rDCM connectivity with white matter tracks, trains an MDN on their directions and strengths, and uses that to generate this 3D flow field. The particle flow you see comes directly from this learned field. The density of curves shows where the MDN found strong, consistent flows. Their orientation shows the preferred direction of information movement through the white matter. What you're looking at is an approximate 3D picture of dominant information flow in the brain, inferred from fMRI, tractography, and the MDN. Even though this flow is still complex, you can now start to build an intuitive sense of how information moves through the brain, almost like watching hidden currents curl and weave their way through a dark ocean of white matter.